Happy morning, guys. Today we shall discuss valence bond theory. So, valence bond theory, there are three theories to describe the bonding in atom. So, it describes the bonding, nature of chemical bonds, right? There are three theories. One is this VBT, and another one is MOT, molecular orbital theory, and another one is CFT, crystal field theory. So the valence bond theory, it talks about the interaction between the atom and explain the chemical bonds here. And other two theories are MOT, molecular orbital theory, and crystal field theory. Before getting into that, we have to know about the ligands, right? As per VBT, the ligands are divided into three types: strong ligands, average ligands, and weak ligands. Let's see one by one. Strong ligands. These are our strong ligands. Strong ligands in the sense it should be a good electron donor. It will donate the electron instantly, and it will always pair the unpaired electrons. Electrons in the orbitals like this: 1, 2, 3, 4, 5. Right. So these are unpaired electrons. Na? This will pair up the unpaired electrons. Right. This will pair up the unpaired electrons. That we will see later one by one. In the central model atom, examples are CO and Cn. Right here, CO is of neutral ligand and Cn is negative ligand. So you have to remember strong ligand. Carbonyl and cyanide are strong ligand. Right. Next we can go for average ligand. This is average ligand. Average ligand in the sense average electron donor. It can act as well as weak and strong ligands based on central metal atom, right? Central metal atom. These ligands can act as well as weak and strong ligands, right? Example: NO2, ethylene diamine, water, ammonia, EDTA, thiocyanate, OH minus, hydroxide. So these ligands are average ligands. And the next type, weak ligands. Weak ligands are poor electron donors and they never unpaired electrons. They never pair unpaired electrons. If there are electrons situated like this, they will never force electrons to getting paired, right? They will remain as it is. And examples: halogens, fluorine, chlorine, bromine, iodine, and sulfide and thiocyanate. We have to understand that the electronegativity of carbon is less than nitrogen, which is less than oxygen, right? So that the carbon will easily donate electrons than the nitrogen. The nitrogen will easily donate electrons when compared to oxygen, because oxygen is highly electronegative than these two things. What can we do with VBT? What is the application of VBT? Where we are employing VBT? So the VBT can tell us about the hybridization, whether it is sp2 or sp3, whatever it may be. The hybridization of CM atom, the hybridization of central metal atom, and spin multiplicity. Spin multiplicity means we can find it out by using the formula 2s plus 1. So this is a spin multiplicity formula. S is nothing but spin quantum number. So S is equal to plus half. Right? S is equal to half here. And magnetic nature of the compound. Magnetic nature is paramagnetic or diamagnetic. And magnetic moment we can calculate by using the formula mu is equal to root of n into n plus 2. So this is the formula to calculate the magnetic moment. N is nothing but number of unpaired electrons. Number of unpaired electrons. So these are the things we can do with VBT, that is valence bond theory. We can find out the hybridization, we can find out the magnetic moment, we can find out the spin multiplicity, we can find out the magnetic nature of the compound. Let us learn this with example. So I think you can name this compound. That is, this is potassium hexacyanoferrate. Potassium hexacyanoferrate. This is potassium hexacyanoferrate. Right. So what is the oxidation state of the central metal atom? So let us start with here. So it is K is plus 1, right? So plus 1 into 4 plus Fe we know, we will take it as yes, x plus minus 1 into 6. So the charge is given as 0. So it will be 4 plus x minus 6 is equal to 0. X is equal to 6 minus 4. X is equal to 2 here. So this is the oxidation state of ion here. So what is the oxidation state of ion here? Plus 2. Let's write the electronic configuration of the central metal atom. Electronic configuration represents ion. It is 26. Atomic number is 26. So the general electronic configuration is argon. That is 18. So remaining 8 electrons are there. It will be 3d4s. So 3d4s2 and 3d6 electron. So this is a general electronic configuration of ion. If it is in plus 2 oxidation state, it will be Fe argon. Fe2 plus means it is argon 3d6 because it is given out these 2 electrons. Here let us taking the ion as X. So we are finding out the oxidation number of ion is plus 2. And here Cn is a strong filled ligand, as I said earlier. So it approaches very fast to the metal ion and it pairs up. It pairs up unpaired electron. It pairs up unpaired electron. So the ligands approaches very fast to the metal atom. They are feeling the repulsion here. Due to repulsion, the electrons get paired up. So the general electronic configuration of ion is 3d6 4s2 4p0. And if for Fe plus 2, these 2 electrons will be removed. So it will be argon 3d6 4s0 4p0. So Cn being a strong ligand, what happens at ligands results in pairing of electrons. So first this is a d orbital, this is 3d orbital, this is 4s and this is 4p orbital. So 3d, how many electrons are there? 6 electrons are there. 2. First actually it should be filled like this. 1, 2, 3, 4, 5 and then the 6th electron will be filled here. So it looks like this, right? When ligand approaches, what happens? The Cn ligand forces this electron to get paired here and forces this electrons to get paired here, right? So then how it will be? This will be, so here 2 electrons, this electrons come and pass here, here 2 electrons and here 2 electrons. Now these 2 places are free. That is 2 orbitals in D is free, D2, right? And how many ligands are there in Cn? 6 ligands, yeah, hexacyanophorate. So 2 plus s orbital 1, that is 1s, and then p orbital 3. So 3p3, 3p orbitals, right? So we can call it as D2sp3. So in these places, the Cn is placing its ligand, placing its electrons. Cn is bonded to the central metal atom, right? So look here. So what happens here? These places become empty because these 2 electrons present here are forced with the Cn ions to get paired with these 2 electrons, right? Where you get D2sp3 hybridization. So the Cn places its ligand. So these are the electrons of Cn minus. These are the electrons of Cn minus. So 6 Cn minus, 1, 2, 3, 4, 5, 6 Cn minus. So the hybridization is D2sp3 hybridization, right? So if there is 6 ligands, what happens? It will be an octahedral complex. Octahedral complex in the sense, so here it is Fe in the center. This is the structure of octahedral. Cn minus, Cn minus, Cn minus, Cn minus, Cn minus, Cn minus. This is the structure of octahedral complex. So structure is octahedral. And the magnetic moment is calculated by using the formula mu is equal to root of n into n plus 2. What is the number of unpaired electrons here and the final stage? Tell me what is the number of unpaired electrons here? There are no unpaired electrons. So n is equal to 0. No unpaired electrons. So then the value will be 0. So Bm means Bohr magneton. And listen here, the inner 3D orbitals, the inner 3D orbital of central metal atom are used. So that it is called inner orbital complex. Listen here. Here, the orbitals will be like this. Now, this is third shell will be here. Let us consider first shell, second shell, third shell, and fourth shell, right? So here, the ligand, CN ligand is bonded in 3D itself, right? 3D itself. So it is bonded with the inner shell, inner orbital, right? So this is an inner orbital, 3D, inner orbital, right? So that we can call it as inner orbital complex because it has bonded with the inner shell, so that we call it as inner orbital complex, right? So let us work it for K3FeCN6, K4FeCN6, right? Shall we work it for K3FeCN6? Okay, let us go with that. So then here, let us find out the oxidation number, that is 3 plus, K is plus, no, 3 plus, so I had written as 3 plus X plus 1 into minus 1 into 6, that is equal to 0. So X is equal to 6 minus 3, X is equal to 3. So the oxidation state of iron is plus 3 here. So let us write the electronic configuration of iron here. Iron 26, electronic configuration will be argon 18. Remaining 8 electrons will be there. So it will be 3D 4s2 2 6. 8 electrons are there. It is 3 plus now. So it has given out 3 plus. So Fe3 plus means argon 3d5. So 2 electrons from s orbital, 1 electron from d orbital has been removed. So it is 3d5. Right. So let us write the electronic configuration. I mean the orbital diagram for 3d5. 1, 2, 3, 4. This is 3d orbital, and this is 4s orbital, and this is 4p orbital, and this is 4p orbital. Right. Now let us fill the electrons. So how many electrons are there? Totally 5 electrons are there. Let me fill like this. 1, 2, 3, 4, 5 electrons. Here what is the ligand present here? Cn. Cn is what type of ligand? This is strong ligand. Cn is strong ligand. So what it will do? It will force the electrons to be paired. Thus the cyanide ion will force electrons to get paired. So these electrons will get forced to pair. So then it will be, the orbitals will be like this. 1, 2, 3, 4. So here 2 electrons will be there, and here 2 electrons will be there, and here 1 electron. These 2 orbitals are empty. Right? So how many ligands are there for CN? 6 ligands are there. So what happens? It can take these 2 orbitals and this one orbital and these 3 orbitals. That is D2 and S and P3. So the hybridization will be D2sp3 hybridization. Right? The hybridization will be D2sp3 hybridization. Let us go for magnetic moment. That is K3FeCN6. Let us go for magnetic moment here. That is mu is equal to root of n into n plus 2. That is a formula. N is nothing but unpaired electrons. Number of unpaired electrons. Number of unpaired electrons. Look at here, how many unpaired electrons are here? 1 unpaired electron. So that is equal to root of 1 into 1 plus 2. That is equal to root of 3. So right. So this is the magnetic moment. You can go for spin multiplicity. Spin multiplicity in the sense that is 2s plus 1. That is the formula. So here S is equal to How many unpaired electrons are there? Only one. So it will be only one half. So the value will be 2 into half plus 1. That is equal to 2. 2 into half plus 1, that is equal to 2. Spin multiplicity. Then nature of that. Nature of that complex. Nature of the complex in the sense whether it is paramagnetic or diamagnetic. So paramagnetic in the sense what it should do. Paramagnetic means it should have unpaired electrons. Unpaired electrons. Whether these are unpaired electrons? Yeah, here there is one unpaired electron. So it is paramagnetic. So nature it is paramagnetic. So it is paramagnetic. So let us go for K3FeCN6. So what we had identified so far. So the oxidation state is +3, Cn is strong ligand, and the hybridization will be D2sp3 hybridization. The hybridization is D2sp3, and magnetic moment is √3, and spin multiplicity is 2, and nature is paramagnetic. Right? That's it. And how K3FeCN6 is prepared? That is, FeCN twice, it is treated with the excess of KCN, K3FeCN6 is prepared. Right? We have to find out its magnetic moment, hybridization, spin multiplicity, nature. So the general electronic configuration is 3d6 4s2, and it has lost out 3 electrons. So 2 from here and 1 from here. So it is 3d5. AR3d5 is a final electronic configuration, and Cn is a strong ligand. So Cn is a strong ligand. So being strong, what Cn's do? Cn pairs up the unpaired electrons. So the electronic configuration will be like this. Here, if it is pairs up, the electronic configuration will be here. So here the d electron will look like. So here, how many electrons? 5 electrons are there. So 1, 2, 3, 4, 5 electrons will be there, and these 2 orbital will be filled. And these 2 orbital and this 1 orbital and 3p orbitals. So this is 2d orbitals na, and here this is 1s orbital na, and here this is 3p orbital na. That's it. So listen here, the cyanide ion places its electrons over here. That is in 2d orbitals and in 1s orbital and 3p orbital. So the final electronic configuration is D2sp3, and it's a strong ligand pairing of electrons. It's from the inner orbital complex because the bonding takes place in 3d orbital, so that it is called as inner orbital complex, and the magnetic moment will be root of n into n plus 2. N is number of unpaired electrons. So how many unpaired electrons are there here? Only one unpaired electrons here. So the magnetic moment is √3. And spin multiplicity, that is 2 into s plus 1. Here we are having only one electron, so s is equal to half here, and the thing is equal to 2. So finally, listen here, whenever the question is asked, you have to write in a clear-cut manner, right, like this. So spin of electron is equal to half, magnetic moment is √3, hybridization is D2sp3, spin multiplicity is 2, nature is paramagnetic. Nature is paramagnetic. Listen here, you know that we had find out this is paramagnetic. Na? You work it out for K2FeCN6. K2FeCN6, that is K2FeCN6. So this will be diamagnetic. So keep it in mind, K3, K4. K3 is paramagnetic and K2 is diamagnetic. Is it clear? Then let us work out some questions. So this will be in your question paper. Find out the complex formed when nickel is heated with carbon monoxide gas. Right? Nickel is heated with carbon monoxide gas. So what will form actually? You have to find out the complex here. What complex should be formed here? And then you have to find out the hybridization, magnetic moment, spin multiplicity, and nature of this compound. Right? Let us work it out. What will happen? NiCO4 will be formed. NiCO4 will be formed. So nickel tetracarbonyl will be formed here. Nickel tetracarbonyl will be formed here. Right. Let us work it out here. what we have to find out? We have to find out hybridization, magnetic moment, spin multiplicity, nature for nickel tetracarbonyl. Right. So nickel tetracarbonyl. So listen here, carbonyl is a strong filled ligand, but there is no charge for carbonyl. The charge of carbonyl is zero. Oxidation state of nickel is also zero here. Right? So let us write the electronic configuration for nickel. Nickel, it is 28, atomic number is 28. So it will be argon, 18 electrons will go on the remaining 10 electrons will be here. So it will be 3d4s. So 4s2, 3d8 electrons will be there. Right? So let us write like this, d orbital. 1, 2, 3, 4. And here this is s orbital. And this is p orbital. This is 3d. This is 4s. This is 4p. Right? There are 2 electrons in the s orbital. There are 8 electrons in the d orbital. That is 1, 2, 3, 4, 5, 6, 7, 8. Right? So what happens? Carbonyl group is a strong field ligand. It's a strong ligand. Strong ligand means what it do? It pushes a s electron to get paired in the d orbital. So the d orbital will be like this now. 1, 2, 3, 4. And here this is a s orbital and this is a p orbital. So here already these orbitals are already filled now. And these 2 orbitals, 3d8 only now, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So these 2 orbitals will be places. So in these places, the 4s electrons are filled. Now, what are the vacant orbitals? S orbitals and p orbitals. So how many ligands are there? 4 ligands are there. So in the 4 places, what will do? The CO will place its ligand in 1s, here and here and here. That is, the CO will place its ligand. So the hybridization will be 1s and 3p. This is sp3 hybridization. So this is sp3 hybridization. sp3 hybridization. And now let us go for magnetic moment. Magnetic moment. That is mu is equal to root of n into n plus 2. So n is nothing but the number of unpaired electrons. Check out the configuration. Is there any unpaired electrons here? No. So n is equal to 0 here. So mu is equal to 0 here. Then spin multiplicity. Spin multiplicity. That is, spin multiplicity means 2s plus 1. Here there is no unpaired electrons. So s is equal to 0 here. So 2 into 0 plus 1, that is equal to 1. So s is equal to 1 here. And then we should go for nature. And nature in the sense whether it is para or dia. Para or dia. Whether does it have any unpaired electrons? Check it out. Whether does it have any unpaired electrons? No. All the electrons are paired. So it is diamagnetic. It is diamagnetic. Right? Okay. So finally we can say the hybridization is sp3 and the magnetic moment mu is equal to 0 and the spin multiplicity s is equal to 1 and it is diamagnetic. Right? So these are the conclusions we are getting from VBT. So let me tell you in a systemized method. Now what happens? Nickel when burns in the blue flame for nickel tetracarbonyl. So general electronic configuration is 3d8. So 3d8 in the sense 1, 2, 3, 4, 5, 6, 7, 8 and these 2 will be half filled. When nickel approaches, it forces these s electrons to get paired up here so that it will get paired up here. Then the carbonyl ligand will place its electron in s orbital and p orbital, that is 1 s orbital and 3 p orbitals. Here the hybridization is sp3 and the magnetic moment is 0 and the spin is 1 and the nature is diamagnetic, right? So this is the thing we can get from VBT. Next, can you do it as your homework? A compound A is formed when nickel reacts with KCl. On treating the excess KCl, a coordination compound B is formed. Identify A and B and give the hybridization, magnetic moment, spin multiplicity, and nature. Shall we work it out? Nickel, when treated with KCl, it gives NiCl2. It gives NiCl2. When treated with excess of KCl, gives K2 NiCl4, right? So this is a compound, that is K2 NiCl4. So for this compound, we have to find what we have to find. Hybridization. First, we have to find hybridization, and second, magnetic moment we have to find, and third, spin multiplicity we have to find, and fourth, nature, either para or dia. So we have to find. So let us check it out. Hybridization. Here, what is the oxidation state of Ni here? Oxidation state of Ni, that is 2 plus x minus 4 is equal to 0. So x is equal to 4 minus 2, that is equal to 2. That is x is equal to 4 minus 2. Or let me write it in detail, that is 2 into 1 plus x plus minus 1 into 4, that is equal to 0. So 2 plus x minus 4 is equal to 0. 2 plus x is equal to 4. X is equal to 4 minus 2, that is equal to 2. So this is here the nickel is in +2 configuration. So let us write the electronic configuration of nickel here. 28, the atomic number is 28. So the electronic configuration will be argon 18, remaining 10 electrons are there. So 3d, 4s, so 4s2, 3d8. So then when it is the nickel 2 plus form, then the electronic configuration is 3d8 only, right? 3d8. So we can write the 3d8 like this. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 places vacant for electrons here, and this is s orbital and this is p orbital. This is 4p, this is 4s, and this is 3d. So here chlorine is a ligand. Chlorine is a weak ligand. Weak ligand in the sense it does not pushes the electrons for pairing. So wherever the place is available, it pairs on. So how many how many chlorines are there? The formula of the compound is NiCl4, right? NiCl4, K2 NiCl4, that is the name of this compound. So 4 chlorine are there. So here one chlorine will place its electron Cl, and here also Cl, and here also Cl, and here also Cl, right? So what is the hybridization? 1s and p3. The hybridization is sp3. Is it clear? The hybridization is sp3. So let us go for dipole moment here. Dipole moment mu is equal to root of n into n plus 2. Root of n into n plus 2. So here the number of unpaired electrons, here 2 electrons are unpaired, right? So root of 2 into 2 plus 2, that is equal to root of 8. And spin multiplicity, that is equal to how many unpaired electrons are there? 2 electrons are there. The formula is 2s plus 1. So that means 2 into half plus 1. That is equal to 2 into 1 plus 1. That is equal to 3. So S is equal to 3 here. The spin multiplicity is 3 here. Right. And the next question is nature. Nature means it will be paramagnetic or diamagnetic. So there are 2 unpaired electrons, so we call it as a paramagnetic. There are two unpaired electrons, so that we can call it as a paramagnetic. Right? So on a nutshell, we can say that the hybridization is sp3. Dipole moment is √8, and spin multiplicity is 3, and nature is paramagnetic. Right? So all the answers will arrive. Let me tell you in a schematic manner. So this is output. When Na plus 2 is treated with KCl, it gives NaCl2 first, and then in excess of KCl, it uses coordination compound K2NaCl4. So the general electronic configuration is 3d8 4s2 for nickel. Na2 plus will have only 3d8. Right? So this is the oxidation number, that is, there are plus 2 here, there are minus 4 here. So plus 2 will be the charge, minus 2 will be the charge of the complex. Cl is a weak field ligand, so no pairing takes place here. So generally, it will be arranged 3d8, the electrons will be arranged like this, right? The chlorine be a weak field ligand, does not have any power to push the electrons here. So it will take the available orbitals. So this one, this S is available, these 3p are available. So it puts there, the chlorine puts its electron there. So it will be sp3 hybridization. How many unpaired electrons are there? There are two unpaired electrons in the d orbital. Magnetic moment, that is equal to root of n into n plus 2. N is the number of unpaired electrons. So n is equal to 2 here. 2 into 2 plus 2, that is √8. Right? And spin multiplicity, how many electrons are there? 2 electrons are there. So 2 into half plus half is equal to 1. So 2 into 1 is equal to 2. 2 plus 1, that is equal to 3. And the thing is paramagnetic. Finally, the nature of the compound is paramagnetic. Let us work out this compound. When Na2 plus is treated with the KCN, gives a compound A, which on treating with the excess of KCN gives the formation of compound B. Identify A and B. Listen here. What happens? That is Na2 plus when treated with KCN, it gives NiCN twice. The excess of KCl, it gives K2NiCN 4 times. So the compound is K2NiCN 4 times. For this, we have to go for hybridization, magnetic moment, spin multiplicity, and nature. Right? So let us work it out. Now, listen here. NiCN 4 2 So this is a complex. So oxidation state is x minus 4, that is equal to minus 2. X is equal to minus 2 plus 4. X is equal to 2. So oxidation state of nickel is plus 2. Right? So the electronic configuration of nickel, EC of nickel, that is Ni28, that is equal to argon and remaining 3d4s. How many electrons are with this already? Na28 means there will be 10 electrons, yeah. So 4s2 3d8. Then Na2 plus means that is 3d8 only. The 4s will be moved. So 3d8. So let us write the electronic arrangement. 1, 2, 3, 4. And this is p orbital, and this is, so that is s orbital, this is p orbital. So here 3d8, in the sense the electrons will be arranged here like this. 1, 2, 3, 4, 5, 6, 7, 8 electrons. So these two electrons will be half full. These two electrons will be half full. So what happens here? The CNS brings its ligand. CN is a strong ligand. So it pairs up the last shell like this. Let me make it much more clear. Listen here. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. So these two orbitals are free. The CN, what happens? The CN, it pushes this electron to make pair with this one. So these orbitals will be like this here. There is 1, 2, 3, and this will be paired here. This orbital will be empty, d orbital. And here this is s orbital, and this is p orbital. So dsp or that. Now it is a tetra compound, that is tetrahedral compound. 4 ligands are there, na? CN4. So one it can take here, only one it can take here, and remaining two it can take here. So it will be DSP2 configuration. So the configuration of this compound, hybridization of this compound is DSP2. The hybridization of this compound is DSP2. So this is a compound formed, and nickel when it is in the 2 plus form, these shells are vacant. Right, the last shell of d orbital, because it is paired up here, last shell b orbital and s orbital and for p orbital. So the DSP2 is a configuration. And listen here, there are no unpaired electrons. So no unpaired electrons means mu is equal to 0. Right? Mu is equal to 0 means there are no unpaired electrons. Spin multiplicity, there is no unpaired electrons, so the spin multiplicity is also 0. Mu is equal to 0, S is equal to 0. And nature, what you have to do, if there is unpaired electron, we have to say paramagnetic. So there are no unpaired electrons, so it can be called as only diamagnetic. And the magnetic moment will be 0, and the spin multiplicity will be 1, and the nature is diamagnetic.